Hello, everyone. Welcome to the AMS Mountain Meteorology webinar series. I'm excited today to have David Whiteman from the University of Utah to tell us about a meteorological conundrum, ice mushrooms on the summit of Patagonia. Also want to announce that the next webinar will be sometime in mid-August, where Mindy Brugman from Environment Canada has agreed to tell us a bit about snow level forecasting in mountains, and in particular, some new Canadian improvements for public safety and climate change applications. And then also excited to announce that we're going to be transitioning the management of the webinar series. So Kristen, Matt Striglum, and Jonathan Mertz, Kristen Rasmussen are going to be taking over managing the webinar series. And hopefully between the three of them, they'll be able to make this even faster and better than I have sort of hacked together for the last few years. So I'm looking forward to see what they come out with. I'm excited to introduce Dave Whiteman, and I'm going to pass it off to him for the rest of this. Take it away, Dave.
Yeah. Okay, I'll share my screen. And the title of my talk today is A Meteorological Conundrum, Mushrooms on Summits in Patagonia. And this is a picture of the Cerro Torre range in Patagonia, in Argentine Patagonia. And there's an odd meteorological phenomenon that occurs down there that is not seen in many parts of the world. I've always been very interested in. So if we look at the top of this peak, which is called Cerro Torre, you see that there are ice accretions that are all along the ridge of that peak and all of the successive peaks. And the climbers, the extreme mountain climbers that have climbed these peaks over the years have called these ice accretions ice mushrooms. And I've been very interested in those over the year. And so that's what we're going to talk about in this webinar. So here we have a view of the Cerro Torre range again. This is from the northwest. And I wanted to mention that my co-author on this talk is Rolando Garibaldi. He's a mountain climber in Patagonia. He lives in the small town called El Shelton, which is the closest town to this climbing area. And he's written a guidebook for the whole area, which is really an excellent guidebook. Rolando has connected me to a lot of climbers in this mountain range and in other mountain ranges of the world who have dealt with these ice mushrooms. And Rollo is well known because he was the first of two climbers, along with Colin Haley, who did the first complete traverse of the Cerro Torre range, starting at Cold Standard that you see here, and climbing successively these four peaks. I'll be showing you some pictures of the ice mushrooms on these four peaks. That includes Cerro Standard, Punta Heron, Torre Egger, and Cerro Torre. The first ascent of Cerro Torre, which is one of the really iconic mountains in the world, was made in 1974 by an Italian group who followed this route that goes up through a whole bunch of ice mushrooms to get to the top of Cerro Torre. There was a false claim to have climbed the peak in 1959, but the actual first ascent appears to have been in 1974. Look at the tops of each of these peaks, and again you see these ice accretions on the top of the peaks and on the ridges. So let's take a look at Cerro Torre from the west side of Cerro Torre. That's the upwind side, since the winds in that part of the world mostly blow from the west. And you can see these bulging ice masses that are on the ridge of Cerro Torre and also on the top. If we take a closer look of the top section, that's what we have on the right here. And on the right, again, you get a better view of what these ice accretions actually look like on Cerro Torre. Well, Cerro Torre is over 3,000 meters high, and that's about the level of the 700 millibar or 70 hectopascal pressure level. So we can often tell something about the weather at the top of that peak by looking at a 700 millibar chart. Let's go down to the next peak, which is Torre Egger. And again, on Torre Egger, you can see the deposition of ice that's occurred near the top of it and the overhanging ice mushroom-shaped features that you see there. On Pine Grande Southwest, we can see a whole ridge. It's a southwest ridge showing the ice mushrooms that the climbers have encountered on Pine Grande, and it's located a little bit farther south than the Cerro Torre range. These rime mushrooms, I think it goes without saying, can present a significant impediment to mountain climbers that are trying to get to the top of these peaks. On Cerro Standart, another of the peaks in the Cerro Torre Massif, we see an ice mushroom here that is kind of overhanging, and it's about 30 meters high. If we go farther south in Patagonia to Tierra del Fuego, we can look at Monte Sarmiento, and you can see again ice mushrooms or ice accretions that have occurred on the top, the sides, and the ridges of this mountain peak. You can also see something that's interesting here, that there tend to be kind of pillow-shaped formations with creases in between. The next peak we'll look at is Cerro San Lorenzo, and there's a terrific ice mushroom on the top of this peak. You can see it overhanging here in the upper right. And in 2000, two climbers lost their lives when the summit mushroom collapsed. Now the next peak that we look at here is Monte Sarmiento. And there we get a better picture of what these ice accretions really look like. And when we look at this, we see that that looks an awful lot like rime formation. That's different from what we get here in the middle latitudes of the northern hemisphere, where we have cornices that form on ridges, and they form on the leeward side of ridges. And these ice mushrooms that we're looking at now are primarily on the windward side of these peaks. So we can form a hypothesis that these ice accretions are really rime mushrooms rather than ice mushrooms. Here's another picture. This is Punta Heron on the west ridge, and we see a giant ice mushroom that is hanging over the kind of the western side or the windward side of Punta Heron. Well, we want to investigate these a little bit further scientifically. No one has ever done that before, and one of the first things we would do scientifically is try to come up with a definition of what we mean by a rime mushroom. So what I've come up with is something that places it in time and space. And so consider a rime mushroom to be a bulge, mound, or mushroom-shaped projection of ice produced primarily by the accretion of hard rime on a surface-based obstacle, such as a summit ridge or mountain face, and lasting more than 1 year and constituting an obstacle to climbing. Now, I say lasting more than 1 year because we often have rime formations, or let's say rime, that occurs, for example, on Mount Hood or on Mount Washington in the United States, but it doesn't last through the whole year. Often it's just something that occurs because of a single storm. Well, what do I mean by hard rime? There's lots of different types of rime, and I'm going to use the World Meteorological Organization's definition of hard rime. So let's go just to that one. Well, by hard rime is a kind of a white granular structure with crystalline branches of ice grains that are more or less separated by entrained or entrapped air. The deposit tends to grow upwind, and the density, of course, is less than that of pure ice because it has the entrapped air in the interstices between the frozen ice particles. To form hard rime, fog or clouds are essential, and Hard rime is formed by the rapid freezing of supercooled cloud or fog droplets, leaving these interstices, and they often form where, or more frequently form where there are moderate or strong winds. Hard rime is rather adhesive, but it can be scratched off if there's just a small deposit. And the interesting thing about hard rime is it tends to form in clouds that have a temperature range between about -2 and -10 degrees Celsius. Now, if the temperature is closer to 0 degrees, then when the supercooled water droplets hit the obstacle, there is a release of latent heat of freezing, which tends to keep the deposition in kind of a liquid state. And if temperatures are below about -10, then there aren't enough ice nuclei in the atmosphere to convert the supercooled water droplets into snow or graupel or sleet. Well, let's look at hard rime again. And let's look at the left figure here. On the left figure, what we have is we have a stake in the ground, or a post, and we have a wind coming from right to left. And as we know, the wind goes to 0 at the ground, and it increases in speed as you get above the ground. The ground, of course, because of friction, reduces the wind right at the ground. So what we find often when we have a post like that is that we have rime feathers that tend to be longer in the upper part of the post than on the lower part of the post. And that's because there are more supercooled water droplets driven towards that post by the stronger winds that are up higher on the post. If we looked at the post from above, so this is the post here, there'll be a flow, let's say, that goes from right to left. It'll be carrying supercooled water droplets, and the bigger droplets will impact on the surface of the post. But because of the separation of the wind going around the post, the small droplets may be carried around the post. So that means that some of the droplets will collide with the post and others will not. Now, down below, let's look upwind of the post, and what we see is these supercooled water droplets which have frozen to the post with the little air layers in between. Now, if there are non-meteorologists in the audience here, I should mention something. That is that in the atmosphere, when you have a cloud that has temperatures below freezing, it is typically the case that the cloud droplets will still be liquid water, despite the fact that the cloud is below freezing. And we call those droplets supercooled water droplets. They'll freeze on impact with a cold surface. Well, when we investigate something like this, it's often good to look to see if there are any equations which might tell us something about the physics. So I have an equation here that people have used to determine the amount of rime mass that forms on power lines. And it's a simple equation. It says that the increase of mass with time on the power line is a function of only 4 factors. The area, the cross-sectional area of the power line, the wind speed that is driving particles towards the obstacle, the liquid water content, that is the water content of the supercooled cloud droplets, that would be in something like a kilogram of water per cubic meter, and alpha. And alpha is simply the collision coefficient. That brings into question whether the particles driven towards the obstacle will be carried away from the obstacle by the flow, or whether they'll impact directly on the obstacle. So it's a number between 0 and 1. And we can maybe illustrate that. I'll illustrate that with a short video, but I just want to mention that when you use an equation like this, it tells you what to look for meteorologically to try and develop evidence that that these are rime formations that are occurring. What you would expect to get a heavy deposition of rime is a strong wind that's flowing towards a mountain, and would have to have many clouds or frequent clouds, they would have to be supercooled, and they'd have to be a certain liquid water content in the clouds. So let's go now to an illustration of the collision coefficient. And here we're going to use kind of a ski jump analogy. Let's consider that the ski jumper is kind of a particle being carried by the wind and trying to get up over a ridge. Let's see. Whoa! That's an example of a collision efficiency of 1. Now, the other thing we would do scientifically is we would look for accounts of ice mushrooms to try to determine where they are in the world, because that'll tell us something about the meteorology that causes these things. So what I've done is I've looked at the American Alpine Journal from 1929 to present, and I've tried to look at accounts, which are often published in that journal, by climbers. And some of these accounts talk about where they have encountered ice mushrooms. I've also, thanks to Rolando Garibaldi introducing me to a number of his climber friends, have got a lot of personal accounts of climbers that have encountered ice mushrooms. They've given me all these really nice photos that you've seen here. I have a huge number of these photos I'm not showing you, but also they've given me accounts of what it's like to climb on these ice mushrooms. And you can also do a web search for ice mushrooms. You get some really odd things when you do that. They don't really show you the ice mushrooms that we're looking for. But climbers come from all over the world to climb on Cerro Torre. And so you have to look for the names in different languages. So we call these ice mushrooms, but in Italian they're called funghi di ghiaccio, and in German they're Eispilzen, and in Spanish they're hongo de hielo. So this is what we found when we looked for ice mushroom accounts. And typically what we find is that there are ice mushrooms that form on isolated islands in the Southern Ocean, in the Antarctic Peninsula, at the south end of South America, in Patagonia, in the northwestern part of Canada, and southeast Alaska. There are also some accounts, and sometimes you don't know whether to believe that they're true ice mushrooms, but there was one account here. Again, it's close to a coast. There have been some accounts in the Himalayas and an account in northern Europe. But typically what we find is that the ice mushrooms tend to occur quite close to the ocean on the western side of continents at high latitudes, both in the northern hemisphere and the southern hemisphere. So let's think about that equation again and look into the meteorology of Rime mushrooms in Patagonia and look for those different factors. So here we look at the ERA interim reanalysis at 70 kilopascals or 700 millibars, about the level of the top of Cerro Torre. We're looking at a hemispheric view from over the South Pole. And the lines that you see here, indicated by these numbers, indicate the height of the 70 kilopascal pressure level. This is a way we often deal with upper air charts in meteorology, as we look at the heights of different pressure levels. And so these are height contours that you see here. And the winds, once we're up off of the ground, the winds tend to blow parallel to these height contours, and they are strongest where the height contours are closest together. Here we have South America extending down towards Antarctica, and we see that in January, which is the southern hemisphere summer, the austral summer, that we have some very strong winds that are approaching the South American continent tip. And we know also that when a strong flow comes over a mountain ridge, there's a speed up effect of about 10 or 15%. So typically what we find then in the austral summer is that the wind speeds are on the order of 16 to 18 meters per second. In July, which is the austral winter, we find that the contours are farther apart and the wind speeds are somewhat lower in Patagonia. Now, this is very different from what we get in the Northern Hemisphere, isn't it? Because we're expecting in winter that we'll have stronger winds aloft, whereas here in Patagonia, the strongest winds are occurring in the summer. So this flow around Antarctica has been called the circumpolar vortex. And those of you who've taken climatology classes have heard the term roaring 40s. By the roaring 40s in climatology, we mean that the wind speeds are very strong in the southern hemisphere between about 40 and 50 degrees south latitude. Now, we're going to take another step here. That last ERA interim analysis, that's kind of a combination of a model and data. But as a meteorologist and an observationist, I always tend to go to look at real data instead of just the model. So what I look for here is I'm looking for radiosondes. Radiosondes are instrument packages carried by free-flying balloons as they go up through the atmosphere, usually launched twice per day. We get back profiles, vertical profiles of temperature, humidity, wind speed, wind direction, and pressure. There are 3 locations in Patagonia that have radiosondes. There's Puerto Montt, there is Punta Arenas, and there's Comodoro Rivadavia. Comodoro Rivadavia is off on the East Coast and isn't really very relevant to what we're doing here. Cerro Torre doesn't have a radiosonde, but again, I've indicated it by a red dot here. And note that Patagonia, or that Cerro Torre is close to the northern Patagonian and southern Patagonian ice caps. The runoff, the melting from these 2 ice caps is very strong and is expected, or is thought to actually account for about 10% of the sea level rise that we're getting across the world. But to the west of Cerro Torre is the southern Patagonian ice cap. There are all kinds of fjords that come in west of Cerro Torre, and there are icebergs that break off the ends of all the glaciers that run out into these fjords. And so there's actually open Pacific Ocean water that's actually fairly close to Cerro Torre, and the mean height of the southern Patagonian ice cap is about 1,500 meters. So I've looked at radiosondes from 1975 to 2012, and I've tried to interpolate to see what things would be like at Cerro Torre or upwind of Cerro Torre. Now here is what I find then. If I look at mean monthly wind direction at the top and mean monthly wind speed here at the bottom, where I've interpolated between Puerto Montt and Punta Arenas to get the Cerro Torre values, which are indicated by the black lines. And what we find is that there are winds, at least the monthly mean winds, are really from the west throughout the entire year. And they are very strong. They are on the order of about 16 to 18, say 15 to 18 meters per second. Now, when we look at this upper figure, we have to keep one thing in mind, that while the monthly average wind direction is almost straight out of the west, that there's a whole series of storms that come around the Southern Ocean. And so there will be a succession of ridges and troughs that will be coming around the Southern Ocean and affecting the weather on a day-to-day basis at Cerro Torre. Now, the other thing we can do is we can interpolate between those 2 sites, and we can try and determine what the temperature and moisture content would be just upwind of Cerro Torre on the Pacific Ocean. And we'll take a parcel having that temperature and humidity, and we will try to lift it up over the southern Patagonian ice cap. And we can do that with a thermodynamic diagram. And as we lift a parcel of air, it moves up to lower pressure and expands and cools. Eventually, it will cool to the point where a cloud will be formed. So when we determine a lifting condensation level, this is a proxy for the cloud base. And what we find in these monthly values is that the cloud base, as it gets lifted up towards Cerro Torre, is between 200 meters and about 600 meters above the ocean surface. As it continues to be lifted up towards Cerro Torre, of course, it will still form a cloud, and the cloud will get denser as you come up over Cerro Torre. Well, now, the other thing that that equation told us, or the information from the World Meteorological Organization told us, was that we have the highest frequency of supercooled cloud droplets where the temperature is in the range from -2 degrees Celsius to -10 degrees Celsius. So I've interpolated again between Puerto Montt and Punta Arenas, and I've estimated the altitude, the mean monthly altitude of the -2 degrees Celsius isotherm. And it is below the height of Cerro Torre, which is indicated by this horizontal line up here. We can also do the same thing with the -10 degrees Celsius isotherm. So what we find is that Cerro Torre, the elevation of the top of Cerro Torre, is in that Goldilocks range between -2 and -10 degrees Celsius for almost the entire year. And now I'd like to talk a little bit about climbing rime mushrooms. We've got some evidence now that those could be ice mushrooms because they seem to fit all of the things that we're looking for meteorologically to determine whether rime would be formed. So when you're thinking of climbing rime mushrooms, and there are several things that the climbers have in their mind. They want to be sure that the anchorage is good in the rime mushrooms. They're interested in the surface characteristics of the rime mushrooms, and they're interested in the internal cohesion of the ice mushrooms. And now I want to mention something for the meteorologist, and that is the climbing has really changed over the years in Cerro Torre, especially since about 2005. And the reason that it's changed is because of a role of weather forecasting. It used to be that the climbers would leave the little town of El Shelton, and they would hike in with a lot of gear to kind of a base camp in some trees below Cerro Torre, or they would build an ice cave or a snow cave up a little bit higher in elevation on Cerro Torre. And they would wait at the base camp until the weather cleared, so they would go up and try and put up a lead or two before the weather came back in bad again. Then they'd go back and wait at the base camp. Eventually they run out of food and have to walk back to El Shelton, and they'd have to resupply their base camp. So it used to be that the climbers then would have kind of an expeditionary style to climb this peak. And they would often have to wait days and sometimes weeks until there was enough of a clearing and the winds got a little bit lower so that they could actually climb the peak. They would often put up a lead or two. They would then fix their ropes. They would rappel down, go back to base camp. And then when the weather cleared again a little bit later, they would go back up and they'd Jumar up the rope, and they would put in another lead or two and so forth. So that's how it used to be done. But it's not being done that way anymore. It turns out that in about the mid-2000s, the internet came to El Shelton, and the climbers could then stay in town, and they could watch the weather, making the forecast themselves out of weather forecast tools that are actually on the internet. And sometimes they would get enough of a warning that there was it wouldn't actually be a warning, enough good news that there was a ridge coming through that might reduce the winds and cause drying and warming. And there would even be people coming from other locations, even from Europe or other towns in Patagonia, to take advantage of those kind of weather conditions. And down below here, I show what resources the climbers have actually used to make their forecast. They've made the forecast themselves because there aren't really specialized forecasts that come for this area from either the Chilean or Argentine Weather Service. They tend to use global climate models. And of course, there's not very good data, meteorological data out to the west of Patagonia. About 71% of the southern hemisphere is covered by oceans. And there's not much data out there, although that has improved a lot since satellites started giving us better data in South America in the 1970s. But they tend to use a global forecast system and also NavGem and the ECMWF model. And here are some comments that I've got from some of the forecasters, which I'll let you read yourself. But the basic thing they're looking for is they're looking for these ridges that come across the southern oceans. And they're hoping that the ridges will come slowly and give them several good days of good weather. When they're down staying in El Shelton, there are lots of nice things down there. There is a really nice place to buy ice cream. You have to kind of struggle up through the town of El Shelton against the wind until you get to that place that sells ice cream. But anyway, there's some real advantages to being in El Shelton instead of in one of these bivouacs. Okay, well, what are these ice mushrooms like? So let's look at this. Here we got two polar bears. We see some footsteps going into an igloo here, and one polar bear says to the other, "Oh, hey, I just love these things, crunchy on the outside and soft on the inside." And that's what the climbers tell me sometimes climbing on these ice mushrooms is like, that they're kind of crunchy on the outside and soft on the inside. There are other ways that you can also get melting on the outside of the ice mushroom. Sometimes it's crunchy on the inside as well. Well, let's look at the anchorage. The anchorage of these ice mushrooms is really pretty good. They very rarely fall off by just coming completely off the underlying granite. Here we have a climber that's making the transition from climbing on granite to climbing on an ice mushroom. This is a difficult transition, as you can imagine, because you use different gear when you go from the rock to the ice or rime. You have to put on crampons and use an ice tool when you get on the rime mushrooms. Well, here's a picture of an ice mushroom. You can look at the surface characteristics, and this tells us something that we'd like to know about these rime mushrooms, and that is we can actually see that there are icicles hanging down from this. So we have to recognize that these are not pure rime, that there are conditions when the rime can melt. There are conditions when there can be graupel or sleet or snow that will pile onto these rime mushrooms as well. So they're kind of a mixed bag, but they seem to be mostly rime. And I'd like to have you use your imagination here for a little while. Let's think about it. Let's suppose you were a climber and you looked at that face, and to get to the top, you're going to have to climb on rime. Can you imagine what it would be like, how scary it would be to climb on rime? Here's a climber climbing on rime. You can see that he's got some protection that he's put in the rime. The climbers will often use a stake, a snow picket. It might be a half a meter long, and they drive it in and hope that if they fall, that protection won't pull out. And there have been a number of instances in which climbers have taken whippers when they're trying to climb these ice mushrooms or rime mushrooms. They might fall 20 or 30 meters. It's a very hazardous thing, because if you injure yourself up here, this is the part of the world that has no rescue whatsoever. There are no helicopters, and it could be a death sentence to get hit by a rock fall or to take a whipper on a climb such as this? Well, the ice mushrooms are quite variable from year to year, and I wanted to show you that. I have two photographs here. This is 1974, and this is 2011. We're from the east side of Cerro Torre here. We're on the windward, or the rain shadow side, let's say. But you can look at the ice mushrooms at the top and see that there's quite a variation between those two photographs. And the other thing I'd like to mention is that there's a lot of interannual and intra-annual variability. After a sudden ice storm, you'll see a lot more rime ice that has formed not into ice mushroom, but just kind of fills up the rock. And you can even see that there are avalanches of rime. When the weather starts to warm a little bit from that, then the rime ice cascades down off the rocks. So there is a great deal of interannual and intraannual variability in the rime ice. Now, there's also some climate change that goes on in this area. There's a huge amount of melting of glaciers. The glaciers have retreated very significantly in some parts of Patagonia, including here near Cerro Torre. Here we have a climber on Cerro Torre, and he's got an ice tool. You see the ice tool that he's got here. Well, the ice tool, the climbers, there are not very many extreme climbers that can climb in mountains, iconic mountains like this, but the climbers have come up with an attachment that they attach to the pick of their ice tools that are kind of heart-shaped things. They find if they're climbing on rime mushrooms that this gives them a much better purchase in the rime so that they can pull themselves up on the ice tool. They've also used these attachments to this tool to actually dig tunnels and half pipes to go up through rime like this. Here's an example of a climber taking advantage of one of these creases like we talked about before. He's probably got a snow picket that's in here. Boy, if he falls, you got to hope that that thing will stay secure in that rime ice. And it's a extremely dangerous and frightening thing to be climbing on these ice or rime mushrooms. Now there's something about Cerro Torre which is very strange to me as a meteorologist. I've never seen anything like this in my life. And that is that there are actually natural tunnels that form up on the ice mushrooms near the top of Cerro Torre. This is the west face. You see these natural tunnels, and you can almost envision that the wind must have had something to do with producing these, because you see these streak lines that come up into these tunnels. And there are a number of hypotheses that people have come up with on how such tunnels form. But it's a peculiar thing, and I don't think anybody understands this yet. So here's a picture of Rolando Garibaldi's friend Colin Haley entering a 15-meter long natural tunnel. And there is, as I mentioned, a lot of variability from year to year in these rime mushrooms. And they're absent in some years, but they're climbable in other years. The climbers prefer these natural tunnels. They're much more secure than out on the surface of the rime ice. So here's a climber who's looking down as he's just exited this tunnel, this natural tunnel. And the nice thing about these tunnels is you feel much more secure climbing in here. And the inside of the tunnel has very good solid ice on the inside. And you can put in ice screws instead of snow pickets. You can feel much safer climbing inside these tunnels. So it is so scary being out climbing on this surface that some of the climbers have resorted to digging their own tunnels when there aren't natural tunnels at hand. So here we have a climber digging a tunnel it took him 4 hours to go 30 meters. Here he is exiting out the top, but it's a much more secure feeling being in the tunnel than climbing out on the Rime itself. Here we have a climber that has been digging with his ice tool. He's dug a half pipe here that turns into a tunnel at a couple of different locations. You can see the scale of these things by looking at Cerro Torre on the right, where there's 6 climbers in the upper part of that. One of the hazards of climbing is that the ice mushrooms hang over the windward side, as you'd expect from the buildup of Rime on the windward side. But sometimes these ice mushrooms will break off. You have to recognize that the ice mushroom is a lot like a snowpack. And you know that metamorphism occurs inside a snowpack during the course of the winter. And there are changes that occur there. And the other thing about a snowpack is that there is glide that occurs in a snowpack. So under the influence of gravity, a snowpack is always trying to slide down the hillside. And sometimes these things will break off. Let's look at a break off. So this is one that occurred on February 27th of this year. And it came from the west side of Cerro Torre. There was a climber, a well-known climber, Dmitry Golovchenko, who was on the southern Patagonian ice cap and whipped out his phone and started taking a video here. Let's see if we can get the video to play. So a climber who might be climbing that west side, the one that was first climbed in 1974, would certainly die if he encountered this ice mushroom breakoff at the top of Cerro Torre. It's produced a snow avalanche, it comes all the way out onto the southern Patagonian ice cap. Well, how big was that Rime mushroom that broke off from the top then? Here we have a picture before and after the collapse. And we think that the size was something like 50 meters by 20 meters by 20. Anyway, it's a fairly good sized piece of the ice mushroom on this ridge of Cerro Torre that broke off. I forgot to indicate the size of that Rime mushroom. Here's a picture looking down on an ice mushroom. This ice mushroom is overhanging, and the climbers have gotten up to the point where they can look down on the top of this ice mushroom. So here's another picture of the top of Cerro Torre. We see a climber here, see an ice mushroom at the top, or Rime mushroom at the top, and a climber here. And you know, there's never really been any observations of how these ice mushrooms really form. The weather is just so awful there almost all the time with very strong winds, and it's mostly in clouds, even though most of the pictures that I've shown you have blue sky, you know. So these pictures have been taken during very unusual weather conditions. But it'd be nice to get some observations. And, you know, if we could just put a graduate student in a kind of a hanging bivouac up in about that location there, I think we could learn a lot about how these Rime mushrooms form. Well, so anyway, what we've done then is we've looked at Rime mushrooms, and there are so many interesting meteorological questions that come from this. A question about this internal ice metamorphism, external questions about crust, phase changes on the crust, collapses, synoptic seasonal interannual effects. Why do they grow upwind? Why do they overhang? Why do they grow vertically? But I kind of bring a lot of these scientific questions into 3 different areas. One is topography, one is cloud microphysics, and one is airflow dynamics. Now, I haven't mentioned this, but I should mention this, that, you know, the whole west coast of South America has a deep channel along the west coast in the ocean. That's because of subduction between the Nazca Plate and the South American Plate. And there is rising cold water that comes up out of this. And so the air that's coming over the southern Patagonian ice cap is preconditioned by its long distance over the ocean where it builds up moisture and the sea surface temperature that's out to the west of Cerro Torre. And my good friend Sharon Zhang has mentioned another thing to me that kind of fits into the cloud microphysics, that you get fairly good size cloud droplets coming up over the ice field because of the sea salt aerosols that form that are cloud condensation nuclei. So that's another thing. But as far as the topography, why in the world do these things form on the ridges? They sometimes form on the faces, but typically on the ridges. So there's all those sorts of questions. There are all kinds of cloud microphysics questions about cloud formation, the aerosol spectrum, the droplet size distribution, other hydrometeors that get added to the rime mushrooms. And then the airflow dynamics are very important. I think they have a strong topographical effect on where the rime mushrooms form. So there are all kinds of really interesting scientific questions. It'd be kind of hard to find a funding agency to maybe address some of these things. I'd like to summarize then by saying that we've talked about rime mushroom examples. We've given a definition of what a rime mushroom is. We've talked about the physics being very much about supercooled cloud droplets and the strong winds that deposit them on topography. We've talked about the global locations of reports of rime mushrooms. We've shown that southern Patagonia is a favored location with extremely strong, consistently westerly winds, with a high frequency of clouds with low bases and a high frequency of supercooled cloud droplets in the size range that produces rime. And we've talked about examples of obstacles to mountain climbing, the texture, internal cohesion, and anchorage of these rime mushrooms, and the existence of the half pipes and natural tunnels that we find on some of these rime mushrooms. And I'd like to acknowledge several students who helped me with the geographical distribution of the rime mushroom, and two people at NCAR who helped me with the ERA interim reanalysis. And most especially, I'd like to thank the climbers who gave me a lot of information about these rime mushrooms and a lot of really spectacular photographs of them. So that concludes my talk, and I'd like to mention to anyone hearing the talk, if you want to hear a little bit more about it, give me a call. You can look me up, Dave Whiteman at the University of Utah, and you can find my email address and phone number there. And I'd love to talk to people about this interesting scientific phenomenon. Some of you may be interested in visiting Patagonia, and I could maybe give you a little bit of information about that too. So thank you very much for your attention.
Thanks, Dave. That was spectacular. I love seeing this stuff. Everyone else on the call, unfortunately, I don't think we have as good a system on Google Meet for letting you raise your hand. So I'm going to have to ask you to try unmuting yourself, and hopefully we won't step on each other's toes. If this gets too hard, maybe we can have people write into the chat. As you're thinking about that, I'll just ask a quick question. I'm curious if anybody has tried to model these things. It's looking at your slide showing all of the dynamics and all of the processes involved. It seems like we have at least a fundamental mechanism of doing so, but I don't know that all of our models would actually, all of the pieces of that would actually come together in a model to produce the rime mushrooms that we see. It would be an interesting modeling test.
It would be, and I'd like to mention that there was a scientist at the University of California at Berkeley who expressed an interest in doing some modeling on this one time, but we never really quite got to it. But you could imagine coming up with some kind of a terrain feature, an isolated mountain, for example, or even just something like a post. And you could put supercooled water droplets in and see how they build up on this obstacle. It'd be a kind of an interesting model attempt, because you would have to change the boundary conditions of the ground or of the obstacle as the Rime ice built up on it. So it's an interesting topic, and I would like to see somebody do that, but I haven't had anybody who's a modeler who's taken the suggestion to try that yet.
Yeah, Dave, a question from Ron.
Yes.
Can you hear me? You hinted there was possibly some theories for those tunnels. Could you tell us a little bit about what people have hypothesized for the tunnels?
Yeah, I can give you some hypotheses. So one that I will often hear from people that I give this presentation to is they think that there is some kind of melting that goes on, and there's some kind of a melt stream that comes down. That is one possibility. The other possibility, the one that I kind of favor, is that as we saw in some of the other mountains, that often these depositions of rime will produce pillows, and there'll be creases in between the pillows. There might be some way that a pillow might grow into another pillow, leaving kind of an opening underneath. Clearly, it looks from the observations that the wind plays some kind of a role in keeping these tunnels open, and also in producing enough melting on the inside of the tunnels that we have solid ice that forms there. So these are two of the hypotheses I can think of right offhand, but I would sure like to hear some other ones as well. It'd sure be interesting to have some observations or some way of evaluating some of these hypotheses.
Thanks, David.
I often will get a question having to do with global climate change, since that's a very important topic. And Rolando, I think he's on this this webinar, has told me he's been climbing there for 3 decades, and he says that the glaciers are rather rapidly advancing. The snowfields are getting smaller. The temperatures appear to be getting warmer. And he's written the climbing guide for this particular mountain range called Patagonia Vertical. You might want to look it up on the web. And his co-author on this is Dorte Pietron, and she's done some work looking at the ERA interim reanalysis, or I guess it's the NCAR-NCEP reanalysis over a number of decades, and she has, of all things, looked at sea level pressure. And she's looked at how sea level pressure, the average sea level pressure for different years, has changed from year to year. And she has found a distinct increase in sea level pressures over that period of time. And so I think that's telling us that there are more ridges that are coming across compared to earlier years when there were more troughs. So we're getting more ridges and more increases of sea level pressure. And along with that, with the ridges that come across are typically warmer conditions. So I think global climate change is having an important effect there. And I think it will have all kinds of effects on the climbers as well. You get more warming conditions like that, you have a lot more rockfall, and there are more dangers from rockfall. So are there other questions? Now, if we have shy people that don't want to speak up in a webinar like this, I wish you'd give me a call. I'd love to talk to you about anything. Maybe some of you even have some trips planned to Patagonia. And just search for Dave Whiteman at the University of Utah and leave me an email message or leave me a phone message or something like that. I'd be glad to talk to you. It's a good time to do that since I'm so bored being here at home with the coronavirus.
Hey, Dave, this is Mindy. I have a couple questions.
Yes.
Okay, the first one is, it seems that there should be some evidence on the mountaintops of past, effects of this, because the summit shouldn't be as affected by weathering or that kind of effect. That was one question. And so if we could see evidence on other mountains around there. And then the other is up above Terrace on the northwest coast of BC. I've been asked by people working up there that why the trees are all flagged towards the west.
Yeah.
And I use the reasoning, oh, well, there's strong outflows, but at the same time, I'm thinking the outflow is really strongest at the valley bottom. So I'm just wondering whether maybe there's other evidence that we could see in trees of this happening.
Yeah. Thanks for those questions. There's a common phenomenon. I'm not sure if it's exactly the one that you're thinking of, but wherever you have a winter snowpack on an inclined surface, there is a long-term drift of snow down that incline. And so when you go into a forest, what you find is that the trees are often misshapen so that the lower part of the tree is bent over towards the downhill direction. And that's produced by this glide or movement, downslope movement of the snow during the course of the winter. So that's one phenomenon that can tend to cause trees that react that way. The other one, of course, is strong winds that occur. Now, when you have very strong winds, this often occurs near valley exits where winds are often the strongest. What will happen is that during the winter, there will be grains of snow that will be picked up out of the snowpack, and the trees will be partly covered by that snow. And often you'll get branches that are on the upslope part of the tree that will be broken off, and the tree will be windswept and bent towards the downhill direction. So that's something that could cause that as well. As far as the top of the mountain and being able to determine something about past events there, it might be possible to do that. I mean, people do take cores in a snowpack or in a glacier to determine when there have been previous episodes of deposition. So that would be possible, but I'm just not sure that would work in a snowpack such as this. So that's kind of an open question with me, I think. But thank you for those questions. Is that sufficient?
Thanks. There just the question, the last one, the one you just answered, the question was about erosion on the rock itself.
Oh.
Ventification and other things. That it should be really obvious if you had that kind of feature there for thousands of years versus you didn't. And then the other one was what the people observed the gal observed was on the tops of mountains above Terrace, the trees were flagged towards the west, and that's the prevailing direction. So it wasn't on the side, it was on the top. So anyway, those were my questions.
Okay. Well, as far as the evidence in the rocks, the top of Cerro Torre is composed of snow, and it never gets down to the rocks, as far as I know. So that's another problem that the climbers have is the ice mushrooms are so deep that they can't really dig down and put a piton into the rock underneath it. So anyway, okay, well, thank you for those questions.
Thanks. It was a great talk.
Yeah.
Thanks. I was going to say, if you have time for one more quick question, I see Justin Minder posted a good question in the chat section, asking if the cleanliness of the southern hemisphere air is important. Specifically, he says, perhaps a low abundance of ice nuclei and or cloud condensation nuclei. Might this help favor supercooled clouds and or large droplets?
Yeah, that's a really good microphysics, cloud microphysics question. And I think it's pretty clear that there is much cleaner air in the southern hemisphere than in the northern hemisphere, where we have so much industrial activity. On the other hand, there is sea salt that is a not an ice nucleating agent so much, but a cloud condensation nucleating agent. So that would produce water droplets. So yeah, that's a good question. There's so many interesting issues like that, and many of them in the cloud microphysics domain.
Well, thank you once again. Yeah, Justin, did you want to get in another?
No, I was just saying thanks.
Yeah, you bet, Justin. Good to see you. It's good to see so many of my old friends on here today. I didn't have any idea there would be so many people that I know. Thank you so much all for coming.
Thank you so much for presenting, Dave. I know I saw something upwards of 60 people on at some point, so you really had a pretty good audience here.
Yeah.
Yeah. Thanks again, everyone. We will have the next Mountain Met webinar by Mindy Brugman there in August. Dino, did you want to get a word in before we end?
No, I just was saying hi, Dave.
Oh, hi, Dino. Wow, it's great to have
Very
you
nice
on.
to hear your talk.
Yeah, well, thank you. All the way from Italy. It's late there at night. It must be 10 or 11 o'clock at night there.
Yes, it's 11, but it's okay. It was worth it.
Okay. Thanks, Dino.
Thank you.
All right. Thanks, everyone. Our next Mountain Met webinar will be sometime in mid-August, and we will hopefully have this posted online at some point for your listening pleasure. Thanks again, Dave. That was truly excellent.
You bet. See you all
Thanks,
later.
Dave. Super cool pictures. Thank you.
Allison, yeah.
Bye.
And Ron is